When we looked at formulas for the directional derivative, we had one formula for 2 dimensions and one formula for 3 dimensions. But it's a very nice formula, and it doesn't take much thought to recognize that both of these are dot products. The first one can be viewed as the dot product of the vector f sub x of xy, f sub y of xy, dotted with the vector AB. But the vector AB is our unit vector that we're dealing with. Same kind of thing for our function of 3 variables. This is the dot product of f sub x of xyz, f sub y of xyz, and f sub z of xyz, dotted with the vector ABC, which of course again is just the unit vector that we're working with. So, and you can kind of notice that these two vectors that we did actually use here don't have anything to do with the unit vector. Nothing in this f sub x and f sub y have anything to do with u. So it would actually be helpful to look at these vectors themselves and just view the directional derivative as the dot product of that whatever unit vector we're working with this particular vector. And so we're going to give this a name. We're going to call this vector, whether it's in 2 dimensions or 3 dimensions, we're going to call it the gradient of our function. And we use this really funny downward triangle for our notation for the gradient. This notation does have a few names, so I do want to first mention those a little bit. The book actually refers to it as del, and that is a fairly common name. But some people do use del for other symbols, and so I find that it leads to a lot of confusion. Um, you in the future, if you're going to be using Calc 3 in whatever context, maybe you'll actually find that people use del more often. I actually prefer the term nabla for this, because that's a completely unambiguous. No one uses that term for anything else. However, whenever we are going to be writing something like nabla f, we're just going to we can just read this as the gradient of f, and that's how we're usually just going to be reading it. There is another notation that is sometimes used for the gradient of f, is just grad f. So think of this as grad is operating on the function f and giving basically a function a vector valued function, you could say. But there are some reasons that we will see in chapter 16 for using this shorter notation using nabla. There are going to be some other similar things that we'll be running into called the divergence and curl that are also going to use this nabla notation. So it kind of, for now, that's the notation we have for it. Later on, we will give it a little bit more meaning. But that's all we have to say about the notation for now. The point is that these vectors, the gradient of f, is just a vector that consists of the partial derivatives of f, and we can do that in any dimension really, but we're working with 2 and 3 dimensions here. We can then, once we have the gradient, we can actually rewrite the formulas that we had at the beginning. So the directional derivative of the function in the direction of any unit vector is just whatever the gradient is times that unit vector. We could even leave off the xy part or the xyz part and just write this as d sub u of f is gradient of f dotted with u. Very nice, simple, short equation that captures both 2 dimensions and 3 dimensions very nicely. Of course, this does require u to still be a unit vector. If we do want to use a different vector v, and I don't know if the book ever uses the directional derivative notation with anything that's not a unit vector. If we're just really saying that this is the directional derivative in the direction of v, and v is not a unit vector, then we just replace the u here with v over its magnitude. But I'm going to stick with working with this first equation and insist on turning any vectors into unit vectors first, just to kind of be more consistent with the way the book is approaching all this stuff. And really, there's not really too much of an advantage of writing down this other formula. This one feels a little clearer, a little bit nicer. So let's go ahead and look at an example. So we have a function of 3 variables. We have a point. We want the gradient of that function. We want the gradient at that point specifically. And then we want to know what is the rate of change in the direction of this vector, or in other words, the directional derivative in that direction. So the gradient of f. Now you could write out all the partial derivatives if you want to. I'm just going to go ahead and write the gradient of f, and I'm just going to stick my formulas in here because we're just dealing with a polynomial. It'll be easy enough just to put those in. So we start off with the derivative with respect to x. Derivative of x squared yz gives a 2xyz. Derivative of x yz cubed just gives us a yz cubed. Now we go with y. Both these are actually a multiple of y, so the y's just go away. We have an x squared z minus z x, or xz cubed. And finally with z, first one becomes an x squared y. Second one becomes a 3xyz squared. So that is our formula for the gradient at any point x, y, z. We can go ahead and plug in our point of 2, -1, 1. And that just put those into these formulas. If we put 2, -1, 1 in for x, y, and z, this first one, which I've already kind of worked out for you, is a -3. The second one becomes a 2, and the third one also becomes a 2. So that's our gradient. We'll give it a little bit of more meaning in a moment. But for right now, what we can do is we can actually look at the directional derivative using this gradient. And we don't have to actually do anything with u here. U is actually a unit vector already. I'm going to leave it to you to actually to show that or to see that. But we will essentially just be taking the dot product of our gradient and the vector 0, 4/5, -3/5. And we just use our dot product formula. We just multiply the x's together, add the y's multiplied together, and then the z's multiplied together. Obviously that goes away. This is an 8/5 and then a -6/5. So we end up with a 2/5. So if you compare that to the work that you would have had to do back in the last video for how to compute a directional derivative, we didn't really save ourselves any work. We still found all the partial derivatives. We still basically, I mean, the whole point of doing the dot product here is this multiplying the components of our unit vector with each of those partial derivatives. We did all the same work, but hopefully the formula and all the stuff that we're going to be doing with the gradient will help you remember the formula for how the actual directional derivative goes. But the real advantage of the gradient may be kind of surprising. let's ask ourselves, among all the directions through a point, in what direction is our function increasing the fastest? I mean, we have all these directional derivatives. Which one's the biggest? So if we view the function as a surface, maybe what we're really asking is, what is the steepest direction if we're trying to climb that surface? Well, if we are just trying to maximize the directional derivative and we're maximizing over all these different vectors, that seems like a really difficult problem. And if we were trying to do it directly, it kind of would be. But if we write it using the gradient, if we use our formula of d sub u of f is equal to nabla f dotted with u, using that gradient, we can use the fact that we have a formula for the dot product in terms of the angle between the vectors. So you could say that this is the magnitude of our gradient times the magnitude of u times the cosine of the angle theta that is between the gradient and the vector u. Well, u is a unit vector, so really this is just the magnitude of the gradient times the cosine of the angle. When is this the biggest it can be? Well, we're really looking at, since the magnitude of the gradient is already fixed, the only thing that remains of the vector u is this angle. When is cosine of theta the biggest that we can get? Well, of course, cosine of theta can only get up to a maximum of 1, and we get a maximum of 1 when theta equals 0. In which case, our directional derivative is actually just the magnitude of the gradient. So that means that the directional derivative is maximized when the angle between the gradient and u is 0, or in other words, when the gradient itself actually points in the direction that the function is increasing. So the gradient is actually giving us the direction of the most increase of our function. And all of this is summarized in this theorem from the book. So if you have a function of 2 or 3 variables, technically we do need here it to be a differentiable function. But if we have a differentiable function, the maximum value of the directional derivative is the magnitude of the gradient, and it occurs exactly when our unit vector is pointing in the same direction as the gradient. And in fact, you can kind of see how moving away from that gradient direction just kind of very smoothly modifies that directional derivative by that angle. We could actually use this formula in terms of cosine of the angle if we really wanted to. But usually we end up just not having to do that. So let's look at this particular function and see what direction does it increase the fastest as we move away from the point 4, 1. Again, that just really means that we are going to look at the gradient of this function. The gradient, we take the partial derivative of this function with respect to x first. So the 4y is a constant. Square root of x, remember, the derivative of square root x is 1 over 2 square root x. Of course, I can go ahead and cancel out part of the 4 and just make that a 2y over square root x. Now we differentiate with respect to y. The 4 square root x is constant now, and the y basically just goes away. We have 4 square root x. If we look particularly at the point 4, 1, if we plug that in here, we have 2 times 1 over square root of 4. Well, that's just 2 over 2, or 1. 4 times square root of 4 is 2, so we end up with an 8. So our gradient is 1/8. That tells us both the direction and it tells us the direction of the greatest change. And if we were to look at the magnitude of this, So that's the square root of 1 squared plus 8 squared. The 8 squared has the biggest effect here. It's 1 plus 64. We have the square root of 65. And that gives us the maximum rate of change as we move away from that point. Let's go ahead and plot this thing and take a look at it. So recall that our function is just 4y times the square root of x. So we got this thing here. Again, let's make this a little bit lighter. Always wants to pick a dark red. I just want it to be a little bit more visible. We go ahead and plot our point. Our point is 4, 1, but we do want to know what the actual z value is. If we plug 4, 1 into our function, so 4 times 1 times square root of 4, that is an 8. And that's a little bit high, so let's actually go ahead and move this down a little bit. There we go. So we have a point on our surface. Actually, let's go ahead and move this. Come on. Yeah, that's a little bit better. Don't have so much empty space visible over there. Okay, so if we want to go ahead and plot our directions, so we start at A, and we move in the direction of our gradient. Remember, our gradient was just the vector 1, 8. That means if we go in this direction, in the looking at the xy plane at least, our function is going to increase faster than any other direction. Of course, that doesn't really actually, you can't really see that on the surface as well. So let's go ahead and actually modify it and actually view that fastest increase. Now we do have to be a little bit careful here. If we are going to plot the vector that it's going to be tangent to the surface in that direction, we do still need to look at a unit vector. In fact, I'm going to rename this because we're using u for unit vector. So let's call that v. I'm going to make a new vector. I'm going to call that u. So the vector is starting at A, moving in the direction of A, plus this same vector, but turn into a unit vector. Remember, the magnitude of that vector is the square root of 65. So I'm going to divide 1 by square root of 65, and I'm going to divide 8 by the square root of 65. And then my actual magnitude of my increase is then the square root of 65 too. And let's make these a little bit darker. Always wants to make them lighter. There we go. So now we have a new vector in there. It's pointing up this way. A little hard to see the whole thing. And now I lost my x and y axes. Maybe we'll zoom out. Maybe that'll help. But we have a unit vector. Well, it's not a unit vector. So if we didn't have the square root of 65 for the last entry, that'd be a unit vector. But it is a vector that is tangent to my surface in the direction of the greatest increase. That's the fastest way you could go up that surface. In fact, we could use that to plot a tangent line if we wanted to. Any of those kind of things. So this is kind of interesting. Well, actually, speaking of tangent lines, we can actually use the gradient as a way to work with tangent planes. There's a couple ways of actually thinking about this. One way is to think of our variable z as a function defined implicitly. So if we essentially have a surface that's defined by a function of 3 variables x, y, and z, set equal to some value k, some fixed value k. What we're really doing here is we're viewing this as a level surface of the function f. Well, if we imagine that we have, so let me just kind of draw on a, we have some surface here. It has some curvature to it, but I don't know exactly what's going on, and that's not really too important. But I have a particular point on that surface. So you have x naught, y naught, z naught. That's on that surface. It satisfies this function. So if I plug those values into f, we get k. If we look at any curve in the surface that goes to that point, so we have a curve. We could call it c, but it's given by some r of t. What happens if we plug this curve into the function? We have capital of f of r of t is going to equal k for any value t that we plug in here. Now this is a composition of two functions. One's a vector valued function, one's a function of multiple variables, but what we can do here is differentiate it. So if we differentiate this equation using our chain rule, remember here that, let me actually put it over here. So our function f depends on x, y, and z, but each of x, y, and z ends up depending on t. When we plug in t into our curve r of t, we get values for x, y, and z that are then being plugged into f. So if we differentiate this with respect to t, just looking at all the different ways of getting to t, well, we have the derivative of f with respect to x times the derivative of x with respect to t. We have the derivative of f with respect to y times the derivative of y with respect to t. And the derivative of f with respect to z times the derivative of z with respect to t. And then, of course, on this side, if we differentiate k, k is a constant, so we get a 0. But really, what do we have here? If we look at this thing, this is a dot product. We have the partial f with respect to x, y, and z. So let's go ahead and write this all out explicitly so we know what we're looking at. But that's then dotted with dx dt, dy dt, and dz dt. But this thing here, the first one, this is the gradient. This is the gradient of capital F. That's what we just defined. So that's very nice. And then this one, you might have to think back a little bit, but this is exactly the way that we compute the derivative of a vector valued function. If we look at r of t, when we differentiate that thing, we just end up differentiating the x, the y, and the z with respect to t. So really, this is just r prime of t. So what this is saying is that the gradient of the function is actually giving us a vector that is perpendicular to the curve. So remember, r prime of t is just a vector pointing along that curve. Maybe I'll exaggerate those vectors a little bit so it's a little clearer. So r prime of t is a tangent vector to the curve, and then the gradient is giving me a vector that's pointing off in this other direction that is perpendicular to it, because their dot product is equal to 0. But there's nothing special about this particular curve. It's just the only thing about the curve is that it is in the surface. And so really, what we're saying is that the gradient of f is perpendicular to the surface itself. Any vector that starts at that point that's in that in that surface or tangent to that surface is going to have at least some curve that where you get that vector as the derivative of that curve. So the gradient is actually giving us a direction that's perpendicular to the surface. We actually will refer to this as a normal vector. So you can say gradient of f gives us a normal vector to the surface f of x, y, z is equal to some constant k. Now, of course, we're working specifically with x naught, y naught, z naught. But the point here is that we have something that's perpendicular to the surface. And recall how we used normal vectors to give the equations of planes. If v is normal to a plane, we have the equation that v dotted with the vector x minus x naught, y minus y naught, and z minus z naught is equal to 0. Basically, the whole point here is that this vector here is supposed to represent any vector in the plane starting at the point x naught, y naught, z naught, and we want that to always be perpendicular to v. So in this particular case, if we look at nabla f dotted with the same vector, and set that equal to 0, this is going to be the equation of a plane that is essentially just going to be the tangent plane to the surface, because the gradient of f is perpendicular to the surface. If we go ahead and kind of expand this thing out, we get this equation. So this is our equation of a tangent plane. And all this really is saying that the gradient of f is the partial derivatives with respect to x, y, and z multiplied by these x minus x naught, y minus y naught, and z minus z naught. And we can also look at the line that's along that normal vector, the line that is perpendicular to the surface, which the book gives in symmetric equations. We can call this the normal line. So we have a plane that's tangent to their surface. We have a line that's perpendicular to our surface. And that gives us a lot of information about our particular surface. Now, of course, in the special case of just z equals a function of two variables, we could actually rewrite this particular equation, kind of just move the z over to the other side, and view the result of that as a function of three variables. So the difference between these has to equal 0 if z equals f of x, y. And so we actually do have a function of three variables that equals a constant. If we look at the derivatives of this, so the derivative of capital F with respect to x, well, that's just going to give us the derivative of little f. Derivative of capital F with respect to y, for the same reason as the derivative of little f with respect to y. And finally, the derivative of capital F with respect to z. Well, that part doesn't depend on z now, and derivative of negative z is negative 1. And so what we get here is f sub x of, f sub x times x minus x naught plus f sub y times y minus y naught. But then minus, because we're using capital F of z, times z minus z naught is equal to 0. And if we move the stuff around, that turns into z minus z naught is f sub x times x minus x naught plus f sub y times y minus y naught. And technically f sub x and f sub y are both at x naught, y naught. So this is exactly the same equation that we had for a tangent plane to an equation of this form. So you can actually view what we've been looking at before as a special case of this more general formula. Just you have to do a little bit of work to put it in the correct form. Let's go ahead and find a tangent plane to a surface. And I guess the book also wants to give us to give the normal line as well. So here we have a function of three variables, x times y squared times z cubed. It equals some function 8, or is equals some constant value 8. I'm going to go ahead and write this as f of x, y, z is equal to x, y squared, z cubed, just to help me out. But we want that to equal 8. And why did you do that? Specifically, we're going to be looking at the point 2, 2, 1. I need the partial derivatives with respect to x, y, and z at 2, 2, 1. Let's just look at the partial derivatives first. Partial derivatives with respect to x, we get y squared z cubed. If we go ahead and plug 2, 2, 1 into there, we end up with 4 times 1, so get a 4. F sub y, this time we get to pull out 2, leave that x, but we have a y and we have a z cubed. Plugging in 2, 2, 1, this time we have 2 times 2 times 2 times 1, get an 8. F sub z, this time we get to pull out a 3, we still have an x, a y squared, now we have a z squared. So f sub z at 2, 2, 1, we end up with a 3 times 2 times 4 times 1. So we get a 24. So our tangent plane we take our derivative with respect to x is 4 times x minus 2. We have 8 times y minus another 2 plus 24 times z minus 1. And that equals 0. Now we could also go ahead and have written this as 4x plus 8y plus 24z, and instead of putting the minus 2 minus 2 minus 1, and then just plugged in our point and see what we got at the end. In this particular case, that turns out to be 48. And of course, we could also simplify this by dividing everything by 4. Everything had a factor of 4 in it. So we could write this as x plus 2y plus 6z is equal to 12. So that's the way I prefer to write it. If you could actually write it as z equals an equation in terms of x and y if you prefer. But I find this the simplest way of looking at it. Our normal line and we're just going to keep using the symmetric equations that the book is using. Not really my preferred way of writing it, but that's the way the book does it, so I'm going to keep it. But remember, we take x minus our x value over our derivative with respect to x. That's equal to the same thing with y, so y minus 2 again over 8. And then for z, we have z minus 1 over 24. And again, the fact that we got 4 as part of all of our partial derivatives, we can go ahead and multiply all these equations by 4 just to make it look a little nicer. So we have that x minus 2 is equal to y minus 2 over 2, which is equal to z minus 1 over 6. So just various things that we can do with the gradient. It's not only a nice way of calculating a directional derivative pretty easily, it also tells us the direction of greatest change of our function, and it also gives us a way to tackle tangent planes. Even though we didn't really write our tangent plane in terms of the gradient in the long run. We just use the fact that it does actually give us a normal vector to make that happen. The book actually goes a little bit more into that. You can, if we're looking at a function of two variables and look at, instead of these level surfaces, we look at level curves. The gradient will give us vectors that are perpendicular to those level curves, things like that. I'm going to leave that for you to actually read for yourself. Um, I don't want to make this video way too long, and the book does actually have some nice pictures, some nice contour maps of that are actually maps and not just pictures of a particular function. That makes it pretty clear what we're actually accomplishing with this idea. But I'm going to leave that here, and I'll see you guys in the next video, the next section.